Richard Feynman gave us one of the most powerful and frankly profound ideas in all of physics, the path integral. It's a concept that completely reimagines how the universe works on the most fundamental level. And it all starts with a very, very simple question. So let's dive in and see how this one idea literally reshapes our understanding of reality.
I mean, it seems almost childishly simple, right? A particle starts here and it ends up over there. But the quantum answer to this question, it completely shatters our everyday intuition and opens the door to a universe that is so much weirder and more amazing than we ever thought possible.
Okay, so think about it this way. In our classical world, if you throw a ball, it follows one single predictable arc. We call it the path of least action. But the quantum world, it plays by completely different rules. An electron, to get from point A to point B, does something absolutely incredible. It simultaneously explores every single possible route. We're talking straight paths, winding paths, and even truly absurd paths, like zipping across the universe and back in an instant. The path we actually end up seeing emerges from the sum, the interference of all of these possibilities. And as we're going to see, this sum over histories isn't just one idea. It's a whole framework for seeing the quantum world.
But here's the thing. To really unlock the full power of this idea, we have to get a little more creative. We have to expand our whole definition of what a path even is. It's not just about where a particle is. As we dig into Chapter 21 of Shanker's Principles of Quantum Mechanics, we'll find that the concept of a path can be so much more.
So the version you probably first learn about is the configuration space path integral. It's the most straightforward kind. Here, a path is exactly what you'd think it is, the history of a particle's position as it moves through space over time.
Okay, but this is where it gets really cool. What if the paths that we're summing up could tell us more than just where a particle is, but also what it's doing along the way?
Well, it turns out they absolutely can. The phase-space path integral is a much more powerful way of doing things. Here, a path is a history of both the particle's position and its momentum. So we're not just summing over routes through space anymore. We're summing over routes in this more abstract phase space, and you're adding this whole other dimension of information to our multiverse of paths. It's a huge upgrade.
It helps to think of all these different types of path integrals, configuration space, phase space, and others, not as just abstract math, but as this powerful toolkit, right? Each one is like a specialized language, perfectly designed to describe different kinds of quantum systems. And picking the right language can make a problem that seems impossible suddenly make perfect sense.
Okay, so you might be thinking, why do we need all these different languages? Why complicate things? Well, the answer is pretty amazing. It's because this expanded toolkit lets physicists tackle some of the most complex and fascinating puzzles in all of modern physics.
And we're not talking about some obscure theoretical problems here. These are some of the heavy hitters in condensed matter physics and quantum field theory. The path integral gives us this unique and incredibly powerful lens for understanding the weird quantum mechanics behind things like the quantum Hall effect, the subtle geometry of the Berry phase, and that seemingly impossible trick we call quantum tunneling.
Take the Berry phase. It's a perfect example of this. Imagine you have a quantum system. You slowly change its environment, and then you bring it right back to where it started. You'd think the system would be exactly the same, right? But it's not. It actually picks up an extra phase. It has a memory of the geometric journey it took. The path integral is just a natural language to describe this beautiful effect.
And this is just brilliant. It really shows you the power of picking the right language. The quantum Hall effect, which is about electrons in a 2D plane with a strong magnetic field, is incredibly messy. But if you use a phase-space path integral and look at the low-energy limit, the problem almost magically simplifies into a one-dimensional system. That is a massive leap forward in our ability to solve it.
All right, I hope you're ready, because things are about to get really weird. Probably the most powerful and strangest tool in this whole path integral toolkit involves a concept that sounds like it was pulled straight out of science fiction: imaginary time.
No, you heard me right. Through a mathematical trick called a Wick rotation, physicists can just swap out the regular time variable t with an imaginary number minus I tau. Now, to be clear, we're not saying time is imaginary. This is a mathematical technique, but it's a technique that transforms the equations into something unbelievably useful.
And here is where the magic happens. When you do this, the quantum propagator, the thing that describes how a particle evolves, becomes mathematically identical to something called the partition function from statistical mechanics, which describes a system's thermal properties. This is a profound, hidden connection. It suggests that the laws of quantum evolution and the principles of thermodynamics are like two sides of the exact same cosmic coin.
And the source material puts it perfectly. In this imaginary or Euclidean time, the whole potential energy landscape gets flipped on its head. An energy barrier that a particle could never ever cross in real time suddenly becomes a valley, and the particle can just roll right through it. These new classical-like paths are called instantons, and they give us this beautiful way to calculate the probability of quantum tunneling.
But the flexibility of this framework? Oh, it doesn't stop there. Not even close. We can actually use it to describe things that have no classical counterpart at all.
Think about something like electron spin. There's just nothing like it in our everyday classical world. It's a purely quantum property. And yet, physicists have figured out how to create path integrals using what they call spin-coherent states to describe how these quantum spins behave.
When we get to particles like electrons, what we call fermions, things get even more abstract. To correctly build in the Pauli exclusion principle, the rule that says no two fermions can be in the same state, we have to use these really exotic mathematical objects called Grassmann numbers. I mean, get this, these are not your everyday numbers. They have this really peculiar property where if you swap their order when you multiply them, you have to stick a minus sign in front. A times B equals negative B times A. And that little minus sign, that's the secret sauce. It's the mathematical key that perfectly builds their quantum weirdness right into the path integral.
So, okay, we've journeyed through phase space. We've dabbled in imaginary time. We've even dealt with these bizarre anti-commuting numbers. What's the big takeaway here? What does it all mean? Well, we've seen that the path integral is far more than just a quirky alternative.
It's that the path integral is so much more than just a fancy calculator. It's a fundamental principle. It's a whole new way of looking at the universe. Instead of a single deterministic story, reality emerges as this weighted average of all possible stories. And this point of view provides an elegant bridge connecting wildly different parts of physics.
I mean, think about the journey we just took, right? We started with a simple question about a particle's path in space. Then, we expanded that very idea of a path to include momentum. We took a wild detour through imaginary time to connect with thermodynamics, and finally we pushed the whole concept into the purely quantum realm of spin and fermions. Each step has revealed a deeper and more powerful layer of this incredible theory.
And that just leaves us with this one final mind-bending thought to chew on. The path integral isn't just a way to calculate probabilities. It feels like a statement about what reality is. It suggests a universe that isn't built on a single concrete history, but on a superposition of all possibilities. What does it mean for our reality to be the interference pattern of a multiverse of potential stories? That's something to think about.